Hello. Performance in GDScript is a concern I see brought up often. I will be showing you how I write scalable code using GDScript. Many people will try to compare GDScript performance with C# or even C++. While this might be an important factor in choosing a language, it still won't matter much in most situations. Even if a language is 100 times faster, it doesn't always mean much when modern CPUs perform billions of operations per second. Often GDScript is used as glue code that calls into functions written in C++, meaning that in most cases, you won't benefit much just by switching languages. You should also account for the time spent debugging or compiling these other languages. There aren't many tutorials online for integrating C# or C++ for Godot. If you are still not convinced that GDScript can handle what your game has to throw at it, then continue watching. Okay, so we're in the editor. Let's configure it to make it easier to compare the performance of our application. So let's come to Project Settings, and in the Project Settings, come down to the Debug section, and in the Settings, you want to enable printing FPS, and then come down to the Display Settings and click on Window. I made my window a little bit smaller because I'm not interested in seeing anything in the window. The other thing I did was to disable vsync. The last thing you'll need to do to set up your environment is to create a new node. Click on node here, and you need to save it. I'll just keep the name as node. And then let's try running it. We'll just select the current node that we just created. And just like that, you can see it's printing the FPS, and we're getting around 3000 frames per second, which is a pretty good start. As you can see, I have a bunch of scripts here, and I'm just going to attach each of these to the node and see how they affect our performance. So just like this, I can drag it and drop it on, and you can see it attached the script here. So in our node, we overrode the process function. This is a function that gets called during each frame of our game. So in this function, I'm calling another function called doWork, which is right here. So doWork is computing an AI 5 times, and in that function for compute AI, I have a function here called delay, which pretty much tells Godot to wait for a certain amount of time before continuing executing. So I use this just to represent some complex logic you can have in your code that takes a long time. But in your case, you would actually have some loop or complicated code here instead. Now that it's attached, we can try running and see how this affects the performance. Okay, let's stop it so we can actually look at the log. And you can see here we have a print statement showing that now we're getting 15 frames per second, which is much worse. It even tells us the number of milliseconds spent per frame, which is 66 right now. Usually you would want that number to be less than 16. So the idea going from here is how you would optimize some code like this. The first thing I want to start with is threads. Threads are a naive approach to improving performance in applications. If you take a quick look, you'll see a lot of the code here is from the previous example. We have a doWork function and a compute AI function. The doWork function changed a little bit. I have a loop here that loops forever. Instead of using the process function, I now use the init function. This is called once the node is created. When a node is created, I call a function called runInThread. The purpose of this function is to create a thread and call our function doWork in it. Now threads are like mini applications that you can run. They run parallel with the rest of your code. I'll attach this new script now and hit run and see what happens. You can see we're still getting printed all these numbers like we were in the previous example. But when I stop it and scroll up and try to find the FPS, our FPS is now back to 3000 like before. So that's a pretty good start. But there's some problems with using threads, and I'll go over them now. There's two documents that I'll cover pretty quickly, just to kind of summarize. the difficulties of using threads. So this first document is specifically about using multiple threads. So in this document, it describes a bunch of different classes that are useful for threads. These classes make threads possible to use, but also much more difficult to use. This is because these classes are meant to control resource management in your system. Doing this incorrectly could actually slow down your code in some cases, and if there's a user error, you could actually even deadlock your code. So because of this reason, using threads becomes a lot more difficult because you need to manage resources like this. Another problem is some of the functions that you call in Godot aren't actually able to be called from threads safely. And this includes a lot of basic functions. Some additional problems with threads is maintaining the lifetime of the thread. For example, in this function, this thread object would be destroyed at the end of the function. Usually that's not a good practice. You would want your thread to live for the entire lifetime of the code that it's running. So in this example, the code runs forever. So not only do you need to manage that, you would also need to manage when to terminate your thread. So you would need to change this loop to have some way to exit. Another problem is that breakpoints do not work when using threads. So if you're used to debugging by putting a breakpoint, when you hit the run button while using threads, you'll see that the breakpoints won't work anymore. And the last problem that I found with threads is that some platforms will have limited or no support for threads, like HTML. So for these reasons, I won't be using threads to optimize our code, but instead, I'll be using coroutines. In this script, I use a coroutine, and I'll be going over how I use that coroutine to execute portions of the code each frame. So you'll see the compute AI function has not changed, and do work no longer has that while loop, but it does now have a yield keyword. Here's how the yield keyword works. When someone calls this function and you yield, you'll return the current state of that function. The caller can then choose when to resume processing of that function. So let's see how it was used below. In the process function, I call run async. In run async, we check a variable called coroutine. If coroutine is not set, we will call our doWork function. In run async, we call doWork. Because doWork will yield, it'll return a coroutine. And on the next frame, when we come into this run async function, the coroutine will exist and we could resume it during that next frame. Let's see how this performs. We're getting 73 frames per second. This isn't too bad considering this code is run in the same loop as all of the other game logic. This is a pretty good start in terms of creating a scalable solution. But if you wanted to configure exactly how this coroutine gets run, it might be difficult to do. For example, if you wanted to configure how often or how long you run this coroutine, you could add extra code to do that. But I'm going to go over a library that I created to help you configure coroutines a lot easier. In order to continue following along, you'll need to install a library that I created called Nylon. If you come to the Asset Lib tab, you should be able to find Nylon by searching. Once you find it, click on it and download. Once downloaded, it'll show up in this section. Click install. First, uncheck all your folders, and then just select the add-ons folder. When you click it, it should select everything, but I already have it installed, so I'll skip this step, but you can click the install button, and then you're done. Nylon's installed. Let's return to our script. Now that Nylon is installed, a new worker singleton is available to us. It provides a function called runAsync, which takes in a function and tells it how many times to run that function. Let's attach the script and see what happens. So you can see in the logs, it executed our function one time, and you can tell because it printed all the different enemies and then printed the done string. Let's start looking how we can configure Nylon, how it runs the tasks. I'll start by using another class called Silk. The Silk class uses the building pattern. The builder pattern allows you to create complex Nylon jobs, but in a much more streamlined way. This is a very simple job. It acts exactly like the previous one. You tell it the job you want to run, and then you submit it to a worker. In this case, I pass the value true here. Let's attach this script and see what happens. You can see now that it executes more than once. That's because of the true value. True tells it to execute forever. Let's just double check the performance. You can see the performance now is still 71 frames per second, which is still a very good number to have. Let's start looking into more configuration options. Let's attach this script. So the first option I want to look at is timed resume. This option will run a coroutine for a certain amount of time. So even if you yield, it'll continue doing work until that time has elapsed. In this case, it'll continue doing work until 2 milliseconds has elapsed. Let's try it out. Okay, let's find the performance. And FPS is still 70. You could try higher or smaller numbers depending on how this affects your performance. Now I'll introduce the delayed configurations. You can choose how long to delay after each time you yield, or how long to delay after each function finishes. This is useful for if functions repeat more than once. So in this example, each time it yields, it'll wait 250 milliseconds. And after each complete function call, it'll wait 2.5 seconds. Let's attach it and see how it works. You can see the numbers coming in a lot slower now. And that was the 2.5 second delay. But our frame has gone up a lot actually. We're back at 3000 frames per second. Let's look at another configuration. This one is the frame configuration. It works very similar to the delayed, except this one takes the number of frames to wait in between. So this will be waiting 16 frames in between each yield, and this one will be waiting 160 frames after each function completes. Let's see what that looks like. We'll attach it and run the script. And we're still getting very good performance at over 1600 frames per second. The next configurations are based around iterators. This configuration is a timed-based iterator. Iterate over a list or any iterable object for this amount of milliseconds. So in this case, if it's not able to iterate through this whole list in 2 milliseconds, it will yield. And every time it yields, because of this configuration, it'll also wait 250 milliseconds. And once it is finished processing all the enemies, it'll wait 2.5 seconds before starting again. Let's attach our script and see how it works. And you can see the FPS is much higher at 3000 frames per second. The last configuration I'll show is based on iteration again, but this is based on batch sizes. In this case, it'll iterate over a certain number of elements and then yield. So it will iterate over 2 enemies and then yield. And when it does yield, it'll wait 250 milliseconds. And then once it finishes processing all enemies, it'll wait 2.5 seconds. We'll attach this one and see how that looks too. Again, we're still getting good performance. Before I move on from configs, there's one last thing I want to cover. So I'll come back here to our simple example. What I want to do is demonstrate how scalable this actually can be. For example, if I increase it to 50 enemies, or even submitted more jobs. Let's attach this script and hit the run button. Alright, and we can pause it and double check how many frames we're getting. And you can see we're still getting a good amount of frames, 60 here. So the main takeaway here is that the work is actually getting done slower because it's more spread out during the frames. But the performance is still pretty stable. One of the reasons this works is because Nylon can be configured to run a portion of its jobs during each frame. The settings can be found in your project settings. Under the Nylon section, you can see here it'll spend 3 milliseconds during each game update processing each of your functions. If at any point it takes too long, it'll stop there and resume your function on the next update. Another useful feature to note is that you can yield more than once. In order to demonstrate that, I will move this delay into our loop and just get rid of our function for now and delete it here too. Let's say instead of one chunk of code, you actually had 2 chunks of code. Now that you have your code separated like this, you could yield twice. Nylon would be able to run this as expected. Also for configs, you can mix and match these values. I would commonly mix and match these 3. I usually want Nylon to spend at least some minimum amount of time processing the job, and then I might add some delay after that job yields. If the job is for something like AI, I don't need to be computing new values too often, so usually I would have a long delay between updates. Now that you have an idea how to configure Nylon, let's go over some useful utilities it provides. When you call submit, a coroutine is returned. Coroutines have many useful signals. For example, completed will be emitted when your job is completed. If you take a look at do work, it returns a value now. This value is returned when the coroutine is completed. Let's attach the script and check it out. You can see it printed all the values, and then it printed the hello because of this print line. Let's look at another signal example. Instead of yielding, I chose to connect to the ended signal. Ended is called at the end of every iteration. So in this case, every time do work happens and returns hello, it'll result in calling this function. Let's attach it and see what happens. And you can see it works just like I described. It iterates through all our enemies and then prints that result due to a signal. The last thing I'll cover is canceling Nylon jobs. The coroutine provides a function called cancel. In this example, I canceled a coroutine after a 1-second timeout. Let's attach the script. And you can see after 1 second, it finished executing. If you look closely though, you'll see that it didn't finish executing all the enemies. That's because I provided a value of false here. If you instead provide a value true, it'll wait until it's finished executing all the enemies. Let's try it out. You can see it reached the done state before finishing. Another option to cancel Nylon jobs is to simply return true from your function. Once done, it'll be canceled immediately. Check it out. See, it stopped after 1 iteration. Before wrapping up, I would like to mention that Nylon is hosted on Github. You could come to the repository and check it out. I have a README with a lot of tips and explanations of all the stuff I covered in this video. And the code is thoroughly documented. If you come to any of the scripts, you'll find plenty of comments that explain exactly how each function and object works. I'll leave a link in the comments for anyone interested in exploring more. That's all I have to say. I'm glad you reached the end of the video, and thanks for watching. If you want to support the channel, feel free to subscribe or like the video. You can also follow me on Twitter, where I challenge myself to tweet 100 tips for Godot for 100 consecutive days. I also have a game I'm working on called Pokemon, which is a poker puzzle game you can wishlist on Steam. Take it easy.